Hi everyone, now let's look at these questions. Okay, the last question in your PowerPoint slide. Okay, so this is a very important questions, and make sure you understand every single steps, okay, of these questions, how you get the value, why the value is like that. Okay, it's very important. So okay, now you have a conducting bar. Okay, so I guess you understand what is the meaning of conducting bar. Okay, can slide freely over two conducting rail. Okay, this is the conducting rail and this is the conducting bar. Okay, as shown in the figure, so you can move it to the right, you can move the bar to the left and right. Okay, calculate the voltage induced in the bar if, okay, we look at question A. The bar is stationed at y equals to at cm. Station means that it's not moving. Okay, it's not moving. Okay, even this is a sliding bar, but for this question, the bar is not moving. It is maintained at the position y equals to at cm. Okay, cm. Okay, and the b is equals to this. Okay, so you can see for this case, right, your bar is not moving. Okay, so it is not motional EMF, but to justify whether it is really motional EMF or transformer EMF, we look at the B. Okay, so can you see here there is a variable T. Okay, so means that the B is a time varying, okay, magnetic flux density. So this category belongs to transformer EMF. Okay, we are going to calculate the transformer EMF. Okay, so for these questions, let us write down. We are going to calculate the transformer EMF. For transformer EMF, what is the formulas? What is the formulas? Right, so the formulas will be equals to negative and, right, integrate, okay, del B over del T, okay, and dot ds. Okay, so it depends on you whether you want to do the integration first or you want to do the differentiation first. Okay, it doesn't matter. Okay, so let's say I want to do the differentiation first. So I want to differentiate my B with respect to T. Okay, so my B, according to the questions, my B is equals to 4 cos, right, 10 power 6 T. Okay, you see an exact here, right? So this exact is actually represent the unit vector Z. Okay, so unit vector Z here. Okay, so for differentiations, nothing happened to the unit vector. You can just maintain. Okay, so for del B, del T, okay, it is equals to 4. So for the cos, you differentiate, you will get sign, negative sign, right? So you will have a negative sign, 10 power 6t. Okay, and for the 10 power 6t itself, you differentiate with respect to t, you get 10 power 6. Right, so this one will be equals to negative 4, okay, times 10 power 6 sine 10 power 6t z, okay, in the z directions. So now you got these differentiations and you put it into your equations. So it will be equals to negative n, okay, integrate minus 4 times 10 power 6 sine 10 power 6t z, right, and over here you have a ds. Okay, so this ds stand for the area, okay, area of your conducting loop. Okay, so why is your area? So this one will be your area, right? Okay, this one will be your area. Okay, if you want to do it fast, because the question already mentioned that it is at centimeter, so this is 6 centimeter. All right, from here to here. So over here it will be at centimeter. Okay, so if you want to be fast, okay, so the ds, you could replace it, you can remain it as ds. You don't need to break it down into ds dy, you can still remain it. Okay, so the ds and dy interval, you can straight away replace it. Okay, and for the n is equals to 1 because we have only a loop. Okay, so I will write down -1. Okay, so -4 times 10 power 6 sine 10 power 6t z. Okay, remember I have a dot product here, okay, which is ds and z. Okay, so my area, my surface area of the loop is facing the z directions. Okay, so over here I will put the area of this loop. Okay, so it is 6 cm times 8 cm. So area, so remember you have to convert it into meter. 6 cm. Okay, so is 0.06 times 0.08. Okay. Okay, so time. Okay, so equals to 4.8 times 10 power -3. Okay, so you put the value here. So area will be from 0 to 4.8 times 10 power -3. Okay, and for the z and z, you dot product two unit vector in the same direction, so it will be equals to 1. Okay, so the value, the answer will be 4 times 10 power 6 sine 10 power 6t. Okay, multiply with 4.8 times 10 power -3. Okay, when you perform the integrations with respect to ds, there is no x here, right? Okay, when there is no x here, when you integrate, you will have x, right? So you replace the value 4.8 times 10 -3 and then 0. That's why you got this. Okay, so you multiply with 4 times 10 power 6. Okay, so is equals to 19200 sine omega as sine 10 power 6 t. Okay, so this is your transformer EMF. Class, over here I missed a symbol. There is a milli. Okay, so this means that this is 4 milli. 4 milli, so I have to include it. Okay, milli. Okay, 4 milli. Okay, milli means -3. Okay, -3, so here I will simplify it as 3. Okay, so over here it will be 3. Okay, and over here it will be 3. Okay, so over here it will be 19.2. Okay. Alright, so now let's look at question B. Okay, so now imagine, okay, the bar slide at a velocity u equals to 20y. Okay, so now it means here now you have this sliding bar, right? And you slide this sliding bar, okay, at a velocity 20, okay, and the directions, okay, y, and the b is in the z directions, okay, 4 milli, okay, 4 milli in the z directions. Okay, so since we are moving the bar, okay, so for this case we are going to calculate the motional EMF. Okay, so the motional EMF. So for motional EMF, the formulas will be integrate u cross b dot dl, right? Okay, so what is our u? So according to the questions, the u is 20. Okay, 20 in the y directions. Okay, so you write down 20 in the y directions. and you cross product with the B. B is 4 milli, okay, 4 milli, right? You can see 4 milli Tesla in the Z directions. Okay, and then you dot product with the DL. L stands for the length. Okay, represent the length of the sliding bar. Okay, so let's look at the sliding bar. Okay, so the sliding bar is PQ. If you want to know the length of this sliding bar, you will refer to the axis X. Okay, so this means that here the DL will be replaced with DX and then X directions. Okay, so next we are going to determine the interval for these integrations. Okay, so let's determine how the current move in the loop. Okay, so now you have a magnetic field which is in the Z directions. Okay, so the current that is produced in the loop will produce another magnetic field that is opposed the directions. Okay, that means it will be in the negative Z directions. Okay, so imagine yourself is holding this sliding bar and your forefinger will be going down. Okay, so your forefinger will be going down, right? Okay, forefinger going down, your thumb will show this direction. Okay, okay, so this is the direction of your thumb, also represent the direction of your current. So your current will flow down, okay, right, and flow in the clockwise direction. So this is the direction of the current. So you are going to integrate from 0, okay, to 6 centimeter. Okay, so here I'm going to write down from 0 to 6 centimeter, and you have to convert it to meter. So it is equals to 0.06. Okay, so let us simplify the unit vector. So y and z is going to give you x, right? Okay, and x is going to give you 1. Okay, so this is going to be 0, 0.06. Okay, so we have 20. So here we have 80 milli, right? 80 milli, and then we have dx. Okay, so it is equals to 80 milli. Okay, multiply with 0.06. Okay, so 80 milli multiply 0.06. Okay, so it's equals to 4.8 milli. Okay, 4.8 millivolt. Okay, so this is the motional EMF. Alright, so now let's look at question C. Okay, now imagine the bar slide at the velocity u equals to 20. Okay, so in this case, okay, the bar is moving, okay, at a velocity 20 in the y direction, and this is the B. Okay, so when we see that you have a u, so this is going to generate motional EMF, but at the same time we look at the B. B is a time varying magnetic field. So this means that you are going to have transformer EMF as well. So the total voltage generated for this case will be the summations of both transformer and also motional EMF. Okay, so let's do this. So now let's calculate the motional EMF first. Okay, motional EMF. So the formula is integrate U cross B dot DL, right, DL. Okay, so the U is 20 in the Y directions, and cross product with the B. Okay, the B, let's see what is the B. Okay, you see it's milli. 4 milli cos 10 power 60 minus Y. Okay, so it's 4 milli cos 10 power 60 minus Y, and in the Z directions. Okay, so the DL stands for the length of the sliding bar, so I will put it as this. Okay, so we will integrate from 0 to 0.06, okay, according to the direction of the current flow. Remember, okay, your forefinger will be going in to generate an opposite direction magnetic field. So your thumb will be pointing this way. Okay, so you integrate from 0 to 6 centimeter. Okay, so let's simplify this. It's going to give us x, and x is going to give us 1. Okay, so here it means that you have integrate 0.06 80 milli, right, cos 10 power 6 t minus y. Okay, and integrate with dx. So you multiply this 80 milli with the 0.06 after the integrations. Okay, so you have cos 10 power 6t minus y. Okay, right, so 80 multiply 0.06. Okay, so you have 4.8 milli. Okay, 4.8 milli cos 10 power 6t minus y. Okay. Alright, so next we are going to move to the transformer EMF. Okay, so for transformer EMF, okay, our formula is negative n. Okay, integrate differentiations of the B with respect to the T and dot ds. Okay, so I would like to do the differentiation with respect to the T first. So my B is equals to 4 milli cos 10 power 6t minus y. Right, so this is my B, which is in the z directions. Okay, so the del B del T will be equals to, okay, so 4 milli here. Cos will give you negative sign. Okay, negative sign 10 power 6t minus y. Right. Okay, and then we will have this 10 power 6. Right, when we perform the differentiations. Okay, and in the z directions. Okay, so I'm going to replace this inside. Okay, so for the n is equals to 1 because on a single loop. Okay, negative 1. Integrate. Okay, so I'm going to combine these two. Okay, so it becomes 4 multiply 10 power 3. Right, I have a negative here. So sine 10 power 6t minus y. Okay, and dot with the ds. Okay, dot with the dx. Okay, so when you have dx, it means that you deal with double integrations. Right, double integrations. Okay, so we have to look at the shape of our conductors here. Okay, how to find the area. Okay, so this is the area, right? So this is the area. The area depends on the value, okay, on the x-axis, which is 6 cm, and also the distance over here. Okay, since this sliding bar is keep on moving, right? It keep on moving. So the y value will put it as a variable y. Okay, a variable y. Okay, so for this case, I'm going to simplify it to be, okay, negative, negative, I cancel it. Okay, so I will write down 4 times 10 power 3 sine 10 power 6t minus y. Right, so the dx is going to be dx dy. Okay, dx dy. So for the x is from 0 to 6 cm. Okay, I convert it into meter, 0.06. And for the y, okay, I put it with the variable. Okay, I put it with a variable. Okay, so for the first integration with respect to the x, okay, we will have 4 multiply 10 power 3 and multiply 0 0.06 because you integrate with respect to the x and there is no x here. Okay, and then sine 10 power 6t minus y. Okay, so this is the y. Okay, right, so we can combine this part, right? So it become, I will straight away combine it to be 0 0.26. Okay, 24. Okay, so 0 0.24 multiply 10 power 3. So I bring it out because it is constants. Okay, so I will integrate the sine 10 power 6t minus y and dy. Okay, so for the integration with respect to the y, the sine will become cos, negative cos. Okay, so you can write down it to be negative cos. Okay, negative cos 10 power 6t minus y. Right, and then you have to divide negative 1 because here is negative y. So you have to divide it with negative 1. Okay, and it's y and 0. Right, y and 0. So the negative will be cancelled out. Okay, so you will have, if I combine it, expand it, it will be 240. Okay, cos 10 power 6t minus y. Right, so this is one minus, okay, so this is one section, right, minus 240 cos 10 power 6t without y, because the y we will replace it with 0. Okay, so this one will be your transformer EMF. Okay, so you can combine your transformer EMF and also your motional EMF. Okay, so the V total, I will write it as V total is equals to, okay, so in fact this you can combine with the, you see, what is the motional EMF? Yeah. It's very small. Okay, it's very small. Okay, 4.8 milli. Okay, so you can write down, okay, 240 cos 10 power 60 minus y plus, wait, it should be minus, right? Minus 240 cos 10 power 60, right, and then you plus the 4.8 milli cos 10 power 60 minus y. Okay, so if you plus this 240, okay, with this 4.8 milli, and it is actually very small. Okay, very small, and in fact you can cancel this part. Okay, you can cancel this part and leave your answer to be this, too small. Okay, when you combine it with the 240. Okay, so this will be the total EMF generated for this case C.